example 3 is really quite similar to example 2. It wants us to find several different compositions, and then graph it and then talk about its domain and range as well. So I think the best way of doing that is just to get into it. I'm not overly worried about the domain and range for f of x and g of x. I'm going to assume that g of x is the same as the previous page. F of x would be all real numbers. I said I wasn't real about it, and now I'm going to talk about them. So the domain for f of x is all real numbers, and the range for f of x is all real numbers as well. For a, because we are doing f of g of x, what f of g of x is going to be is I'm going to take function f and replace the variable x with the function x squared. But then the plus 1 is still there. So f of g of x is just going to be written as x squared plus 1. And I really do want to highlight that all I've done here is taken the function g of x, which is x squared, and put it into the variable in f. If there is multiple locations the variable is, or multiple locations the variable are, anyway, English doesn't matter, you have to substitute every variable in the outer function with the inner, g of x or 2 or whatever it tells you to. All right, so f of g of x is x squared plus 1. That's hopefully not too tricky. That's just the parabola y equals x squared shifted 1 unit up. This is why we spend a lot of time on those transformations, because it does give you the ability to do some of these questions without touching a calculator, which I think is important. And this function has the domain x is an element to the real, but the lowest point, the vertex, is at 0, 1. So y is greater than or equal to 1 and is an element to the real. Not too bad, I think, and that's typically not the one that students struggle with here. For b, it wants us to figure out what g of f of x is. So g of f of x, I'm going to take function g, which is x squared, but it's not x anymore, it's function f. So that's going to be x plus 1. Now, a lot of students will see that x plus 1 squared, and they'll want to expand it. They'll want to write it as x squared plus 2x plus 1, and that's not wrong. X plus 1 squared does expand into x squared plus 2x plus 1, but it's actually much better to leave it as is. Because what I can look at, if I look at x plus 1 squared, then what I'm going to treat that as is the graph of x squared shifted 1 unit to the left. And I'm going to write it a little different, just so we can make that connection with our transformations, that you could write this as x minus negative 1 squared, therefore h is negative 1, so there's a horizontal translation 1 unit to the left. And what that graph looks like, roughly, is this. I do know that the vertex is right here at negative 1, 0. Therefore, the domain is still all real numbers, right? That horizontal translation isn't going to change that, but the range is that y is greater than or equal to 0, and y is an element to the real. All right, I always kind of run out of room here, so I'm just going to try to carry it down a little bit. I'm going to write these because I do always forget them when I do this question. So f of x is equal to x plus 1, and g of x is equal to x squared, and so c is f of f, and d is g of g. I think I can remember that. Maybe I'll write them down right away. So c is going to be f of x, and d is going to be g of x. Kind of a nightmare to say, I know, but we have to get used to this type of function composition. So function f evaluated at function f is a little bit tricky, and I would always recommend that you picture it as, okay, I'm going to put a bracket where the variable was, and what I'm going to do is inside that bracket, I'm going to put function f, which is x plus 1. Now, all I've done here, and maybe I'll use it kind of capital in green, function f is x plus 1. I replaced the x that I did a capital X with the entirety of function f. So the x plus 1 replaced the variable in my function f, and therefore I can say that f of x is equal to x plus 1, which is x plus 2. And what that graph looks like is a linear line with a slope of 1 that passes through the point 0, 2. You got to love linear equations because they are just x is an element to the real and y is an element to the real, unless there's some other restriction involved. Okay, for g of x, I'm going to try to write it in the same way because, maybe I'll go one line lower here, because g of x is the variable squared, that's this piece up here, I'm going to write this with kind of a decent amount of space because you never know what you have to put in there, and I'm going to write it as something squared. Now, I should say it's not really something squared, it's x squared, but that's g of x. G of x is the function g squared. Now, we know that the function g is x squared. So I'm going to square x squared, and I get that g of x, when we apply that power and a power, we multiply. So this will be x to the power of 4. Now, again, this is some of those previous chapters, haunting us a little bit at the end here. You should know what x to the power 4 looks like. It is just a fourth degree polynomial with a positive leading coefficient. So what it looks like is basically this. It should be a little flatter than a parabola, but we're not going to mark you too much. We would use technology if we wanted an accurate graph. And I'm going to say that x is an element to the real, but y is greater than or equal to 0 as an element to the real. This question is essentially in here just so we can deal with that function put into itself, which is a very valid composition, and it's just some of that notation that we have to get used to.